As I said, it's a bit daunting to follow Professor Katani and Kuramoto-san after their excellent introductions. And I'm really disappointed that I'm not there in person, but due to circumstances that ended up being beyond my control, I am sitting in my basement in South Bend, Indiana. But I feel very, very honored to be present virtually at this symposium, and I want to share a little bit with you about what the research I've been following and how it's now marrying my scientific ocean drilling with my planetary research. And basically, a subtitle to my talk is Plume Volcanism equals Planetary Volcanism. And this is what I want to talk about during this symposium. So the Earth is unique because we have water. It's the blue planet. It is home to the only life that we know of in the solar system and maybe beyond. And it also has plate tectonics, which is not present on any other planetary body in the solar system. And this is important. This makes the Earth, these three things make the Earth unique in our understanding of planetary systems, and also in terms of volcanic activity, because Earth has volcanism due to plate tectonics along plate boundaries, but it also has plume volcanism, which doesn't obey plate tectonic theory, although it may be linked to it. If we look at plume volcanism on Earth, it's due to transfer of heat across a boundary. This could be the core mantle boundary or the upper mantle, lower mantle boundary. And it brings unprecedented flood volcanism to the surface. And we see those dotted throughout the continents and the oceans as continental flood basalts or oceanic plateaus, but also these hotspot volcanoes, the volcanic chains in ocean basins, as well as on continents. The plume rise could be initiated through subducted material reaching this boundary, maybe the core mantle boundary in some of these larger flood basalt provinces, initiated plume material or hot material rising from there. And these large igneous provinces are correlated with large low shear velocity provinces at the core mantle boundary and into the lower mantle. These could represent a thermochemical pile at the core mantle boundary. But what I want to focus on here is what makes these thermochemical piles such that we end up seeing these unprecedented volcanic outpourings at the Earth's surface. But the plume volcanism on other planets where we don't have plate tectonics, how does that work? Why do we have big plumes on other planets, but no plate tectonics? I don't plan on answering the why no plate tectonics, but I do wish to propose an avenue by which we can address what actually forms a large low shear velocity province to initiate the architecture for plume volcanism. So if we look at Earth, we have two large antipodal LLSVPs, one around and under Africa and one in the Pacific. If we look at large igneous provinces on Earth, they're dotted around the globe and they have a large range in ages, and they look like they have an irregular distribution. But if we do a paleogeographic relocation, they tend to cluster along the LSSVP margins. And these LLSVPs appear to have long-term stability, and they are dense and hot. They are compositionally subdivided into two domains, a primordial bottom domain near the core mantle boundary, and what is termed a basaltic shallow domain that extends from 1,100 to 2,300 kilometers depth. Now, this is all done through geophysics and understanding the velocity profiles at the core mantle boundary and just above that. These double layered piles exist for billions of years, and they can do, if these density differences are quite large, short-lived secondary plumelets rise from the roofs of the LLSVPs, and we see these short-lived plumes occurring have a surface expression in the oceans. But long-lived, vigorous primary plumes tend to come at the borders, as seen when we did the paleogeographic relocation of large igneous provinces. And again, the model that has been produced by Balmer et al. Is consistent with the locations of hotspots relative to LLSVPs and address the geochemical and geochronological record of oceanic hotspot volcanism. So this seems to be a robust correlation. But this two-layer LLSVP, what's the origin of this material? So we have a basaltic-rich upper portion separated supposedly from deep subducted lithosphere, and this has been shown geochemically by Yaoling Niu, 2018, and Fan et al. 2022 did some modeling to show that it's consistent with the geophysical data that are available. What else can cause these? Wang et al. 2021 has talked about a decomposition of oxidized mantle, and if you have iron-rich bridgemanite, which is a magnesium silicate in the perovskite structure deep within the mantle, and it can explain, if it's iron-rich, it can explain some of the observed features of the geophysical features of the LLSVPs. What about the periditic or komatiitic layer, the primordial layer? And this is where it gets interesting from my viewpoint in looking at having a planetary viewpoint on this subject. It's some of the ideas for this is that they actually represent the magma ocean cumulates after the initial formation of the planetary body underwent a magma ocean differentiation and ended up with the cumulates that formed the initial mantle. But some of these seem to have been trapped at the core mantle boundary, and this is something that could, in some planets, delay or prevent plate tectonics, but for some reason did not do that on Earth. The idea of primordial magma ocean cumulates has been further advanced to the papers cited here. And these are these compositionally dense leftovers from the magma ocean phase. And they form dense accumulation piles by mantle flow. And those dense piles represent stability over billions of years. So if we take a broader view beyond Earth, you can see in the bottom right picture, we've got the Hawaiian Emperor chain with the bend there between the two ridges. This has been proposed to be due to hotspot movement. But if we look at Venus, we have linear chains of pancake volcanoes that have been imaged through radar. On Mars, we have Olympus Mons and the Tharsis volcanoes that represent hotspots. And then Mercury, we have flood basalts as represented by the Chloris Basin lava flows and the caldera that has been imaged there. So the question is if the plume volcanism on Earth is due to subducted material reaching the core mantle boundary and causing disruption of the LLSVP at the edge of that would then cause hot materials to rise. How is it initiated on these other planetary bodies where there's no plate tectonics, and yet we still see the surface expression of plume volcanism? So if we look at Earth again, we see that, okay, well, we've got subducted material. That's unique to Earth. But if that's the case, if LLSVPs are present on other planetary bodies, and we don't know that, then the subducted material on Earth is something that gets in the way of understanding the true origin of plume volcanism, because you just won't find it on Mars, you won't find it on Mercury, and you won't find it on Venus or even the Moon. So the hypothesis is that LLSVPs represent evidence of the primordial differentiation of terrestrial planetary bodies through an initial magma ocean stage, and these are responsible for plume volcanism. The fact that we have subducted material there is the fact that we have plate tectonics, and it's not to do with the doesn't really have a driving mechanism for plume volcanism. So we can't test this hypothesis on Earth because, again, we've got a long-lived heat engine that has caused a lot of material to move around, but we also have the material, the subducted material down there that is blurring the picture. We really can't get a good view of that. And it's difficult to test on other planets for the same reason, because of the larger size and the heat engine, which has caused evolution. And it's very difficult to set up a geophysical network on other worlds. So we look out and we can see now just over a half moon as the moon rises. The moon is ideal for testing this hypothesis, and this is something that I want to spend the rest of the talk on, because I think if we look to our moon, we may have a way to understand how plume volcanism is truly initiated throughout the solar system. If we look on Earth, again, you can see in this descending slab here, this is something that we won't see, and I think it is just a complication to plume volcanism, to understanding plume volcanism by using the Earth as a laboratory. So for those of you that aren't familiar, the moon, if we look at the near and far sides, as you can see there in the diagram, the dark areas represent Mare or flood basalts. These are mostly on the near side because the crust is thinner, and these are derived from a mantle comprised of magma ocean cumulates. The moon is a small enough size that the initial differentiation is probably still preserved in the interior. And the white crust is due to plagioclase flotation cumulates during that initial magma ocean phase. So we have a differentiated source for our basalts. And if you look in the middle rare earth element diagram here, we can see that most Mare basalts, in fact, almost all Mare basalts, have this ubiquitous negative europium anomaly, which represents processing, i.e. plagioclase has been removed. Now, Mare basalts do not have plagioclase as an early liquidus phase, i.e. they're not fractionating plagioclase, which would remove europium 2+ and give you that negative europium anomaly. So this is inherent in the source, and it represents removal of plagioclase during the magma ocean phase. There are a few complications to that, but what we see is ilmenite comes out last, which is a dense iron titanium trioxide, and this causes density instability, and we end up with a cumulate overturn that would send the denser material down, potentially to form LLSVPs that remain stable after that initial differentiation, not only on the moon, but on other planets. But on the moon, we think that this may be preserved at the core mantle boundary. If we look at the basaltic materials, you can see a range in titania contents from less than 1%, which represent very low titanium basalts, from 1 to 5% or low titanium basalts, and then greater than 5 weight percent, which represent high titanium basalts. Now, these contain a lot of ilmenite in their source region, these high titanium basalts. So this overturn that's depicted on the right here represents a mixing of early and late stage cumulates, and possibly sending some of these denser cumulates to that core mantle boundary. If we then look at the surface, and we can get an idea of ages of the different basalt provinces by just looking at impact craters. The more impact craters you have, the older the terrain. We have Apollo sites where we have samples, so we can constrain some of those, and we can get an idea of ages, and then we can get an idea of volumes of these basalts, which I don't have time to go into. But what it does is it allows us then to look at the peak of Mare volcanism. And you can see that there was a high effusion around about 3.6 and 3.4 billion years ago. In fact, high enough, it's hypothesized that there was actually an atmosphere on the moon at that time due to outgassing that went along with the volcanism. So this is at the extent of flood basalt volcanism. And if you look at the diagram on the right, you can see here the younger basalts occur in this area around Mare Imbrium, which is this big circle. This is called Oceanus Procellarum. And the Mare Imbrium and Oceanus Procellarum are important because they have a surface expression that shows a high thorium content. And you can see here is the Imbrium terrain. This is Oceanus Procellarum down here. And we can see that there's a high thorium surface content right there, identified from Lunar Prospector mission from the late 1990s. And the youngest volcanics occur in this Procellarum creep terrain. This has been modeled to suggest that there was plume activity pretty much after about 4 billion, younger than 4 billion years. And this has continued basically to about 1 billion years. And this is consistent with the ages that we see in some of those basalts in the Oceanus Procellarum and the Procellarum creep terrain. So verification of the origin of these plumes can come through geophysical data. And we do have geophysical data from the Apollo missions. And you can see the Apollo network of seismometry in the yellow here, with Apollo 12, 14, 15, and 16 forming a very narrow network on the lunar near side. Now, they detected 4 types of seismic events on the moon: thermal moonquakes, which is basically associated with heating and expansion of the crust, and then the contraction of the crust as the night-day, day-night terminator crossed the landing site. And these represent low magnitude, lowest magnitude of all moonquakes. Deep moonquakes are, many of those were recorded, many coming from unique nests, giving unique seismic signals, and these associated with tidal forces. Many occurred due to meteoroid impacts, and a lot were detected during the Apollo network lifetime. And then we get these interesting ones, these shallow moonquakes, which have magnitudes greater than 5. And statistically, one of those events occurs every year on the moon, one of which occurred close to the South Pole, where the United States wants to put a base camp, as does China. Now, these shallow moonquakes give you a maximum ground amplitude that lasts for 10 minutes, much longer than any earthquake. I heard the safety announcement: if there's an earthquake, what to do if you're there. If there's a moonquake that lasts for 10 minutes of magnitude 5 or greater, and you get a crack in your habitat, then you're going to have a really bad day. So these understanding these types of seismicities become very important. But the network was too close to detect deep mantle and core structure. So we need to reevaluate and maybe reestablish a wider network. So this has come to the attention of the national academies here in the United States, and the Lunar Geophysical Network mission is now a high priority mission in the science mission, and has been in NASA's last 2 decadal surveys, i.e. figuring out what we're going to do at the moon over the next couple of decades. And this is now a named medium class mission in the New Frontiers line. And a planetary mission concept study was funded in 2019, and it was found to be feasible, and it will be proposed in 2024 with the New Frontiers 5 call when that comes out. And this will aim to have a globally distributed network of seismometers, heat flow probes, electromagnetic sounders, and laser retroreflectors to study the internal structure and composition of the moon. The goal is to understand the initial stages of terrestrial planet evolution. And when I was putting this talk together, it suddenly struck me that this mission will be in an ideal position to test LLSVPs and plume volcanism. So this will be added as one of the objectives to this mission. You can see here we're going to define the internal structure of the moon, constrain the interior and bulk composition of the moon, delineate heterogeneities within the interior as they relate to surface features and terrains, and evaluate the current seismotectonic activity of the moon. But if we look at the distribution, these are now globally distributed, and hopefully you can see the inverted triangles here. This one is on the far side in the Korolev Basin. This is in the Procellarum Crete terrain, and the near side, Shikard Basin, and over here in Mare Crisium. Now, these have been chosen because of what we know, what Apollo showed us about deep moonquake nests. And many of these, or these sites are transverse or antipodal to deep moonquake nests, so we can actually trace the seismic rays through the interior of the moon to understand the core mantle boundary. And again, this is just a paper published. Scientific rationale for these sites is out in this paper right here. So we hope then to actually make inroads into understanding LLSVPs and their contribution to plume volcanism by studying the structure of the moon, because it will be uncontaminated by plate tectonics. Because plume volcanism is the norm on rocky planetary bodies. On Earth, plume volcanism is associated with LLSVPs that contain accumulated subductive material. But the question is, how is plume volcanism initiated on other planetary bodies? So the ultimate origin of these LLSVPs could be, and I put is here, but could be due to cumulates from the initial planetary differentiation via a magma ocean. The Earth story is confused because of subsequent accumulation of subducted material. So we can test this hypothesis on the moon through the Lunar Geophysical Network mission, because the moon has experienced plume activity. We see flood basalts. We also have this very enigmatic thorium anomaly, which could represent a heat source at depth, because that's where we also see the youngest basalts, where the Chinese landed at Mons Rumke and brought back basalts much younger than Apollo, which were all older than 3 billion years. And the ones from the Chinese are 2 billion years. And the lunar interior preserves the magmatic ocean cumulates, because we see that in the source regions of the Mare basalts. So we have an opportunity to not only advance lunar science, but also to advance our understanding of the deep Earth by reaching out to our nearest neighbor and looking at that, because that doesn't have plate tectonics to confuse the situation. And that is my talk. Thank you very much.